All right, so what we're going to look at is integration by substitution with definite integrals. So the kinds of questions you might want to be answering are ones like this, where you've got the integral from 0 to 3 of some function going on, but you want to make a substitution so that you can make the integration a little bit easier. So I'll just do a worked example here. There is a bit of prior knowledge here. Before you do this type of thing, you probably want to go back and have a look at some previous videos just around U substitution. And you probably need to know a few things just in terms of the power rule for taking the integral of a function. Because when you get given something like this, which is clearly the product of sort of two functions, 4x and then the square root of x squared plus 9, you need to be able to simplify it so that you can take integrals with the rules that we're sort of familiar with up to this stage. So I am going to jump into sort of working it out, but then I'll show a picture because I think that'll be helpful. So first thing to say is we want to set u equal to x squared plus 9. So you're going to set u equal to the thing that's easy to sort of differentiate. And you're sort of looking in terms of the structure of the what's inside the integral there. You're looking for something where if you were to take the derivative of u with respect to x, it would give you du dx, and then that du dx is somewhere else inside the function. So let me show you what I mean. So if we set u equal to x squared plus 9, then we can say du is 2x dx. Or another way to think about that is the derivative of u with respect to x is 2x, and then you just move the dx to the other side. You can sort of treat it as a fraction. I'll put a link below for sort of why we're allowed to do that. But we can see that du equals 2x dx. Okay, and then if we just multiply both sides by 2, we can see that we get 4x dx would be equal to 2 groups of du. So this symbol here means it implies that. So we can say that this equality is also true, given that this is sort of what we derived from here, right? So what we're saying is, this 4x part is kind of, structurally, is kind of like the derivative of this part underneath the square root, but just multiplied by 2. So we've sort of got this information at the moment. What we want to do next is work out our bounds. So essentially we're doing, again, what's a u substitution. So we've got this x situation going on where these are the bounds on x between 0 and 3. But we know that u is equal to x squared plus 9. So for this lower bound, if we substitute x equals 0 in there, we get 0 squared is 0 plus 9 is 9. So if x is 0, then u is 9. And similarly, just putting the x equals 3, the upper bound into here, you'll get 3 squared, which is 9 plus 9, gives you u equals 18. So you can start to see we're making this transformation where now we've got, u and instead of x. So what that might look like is this, okay? So just pause for a moment, take a moment to digest sort of how we came about that. But basically we said the bounds are going to be now between 9 and 18. We know that this square root part, it's just the square root of u because u is x squared plus 9. And we know that the remainder, 4x dx, is just 2 groups of du. So you've got the 2 here, and then you've got the du there. And that's really the heavy lifting part of this problem, because now we actually should know, hopefully if we know the power rule of integration, how to integrate something like this with respect to u. So if we do that, we'll actually get this. And I'll just explain this quickly. Hopefully you know your index laws in terms of the square root of u is 2, or I should say in this case it's 2 times the square root of u, which is 2 times u to the power of 1/2. Okay, if we just ignore the 2 for now, if we were to integrate u to the power of 1/2, you bring the 1/2 down, add 1, and then do 1 over that. So it's 1 over 1/2 plus 1. 1/2 plus 1 is 3 on 2, or 1.5. 1 over that is 2/3. And then you multiply it by 2. So 2/3 times 2 now is 4/3, and then u to the power of 3 on 2. And this is our antiderivative of this function. And we know now that we're doing it between 9 and 18, because these are our new bounds, right? And so if you crunch the numbers on that, you will get this. And remember, when you're computing a definite integral, you substitute in the upper bound for u in this case, and then you subtract the lower bound substituted in. And so you'll get something like this, and our final answer simplifies to 72 root 2 minus 36. And the whole reason I want to sort of show this, this video is to sort of see the transformation that occurs if we were to graph it. So at the moment in blue, we've got the original function, and we've got our x-axis here. So if we were to sketch it between 0 and 3, we can see that this area here is the area that we're interested in. It's the area, how much area is there between 0 and 3 of this function. And that's just what it happens to look like in that region. But what we just said was, all right, this area is the same as the area underneath the function between 9 and 18 of the function 2 root u du. So if we look at what that might look like, we can see that if we create a new function g of u, then that's now what's on our y-axis, and we've got our u-axis here. So we can see that area has sort of been transformed to be this area, which is much easier to compute. And I think when I first learnt about sort of this u substitution method, I didn't really feel why it was true. It just felt a bit algebraic and not connected to any sort of, you know, picture reality. But the way I see it now is that, yeah, we're sort of changing the x-axis to the u-axis and then finding the area underneath an easier function. So yeah, hopefully you found that interesting. If you did, give us a thumbs up and subscribe as well. Yeah, these videos are fun to make, but they're hard work. So if you can, yeah, support as much as possible, that would be great. Yeah, hopefully good luck to all the people doing their, you know, methods and specialist and general exams coming up. Hopefully one day I'll have most of the course in terms of the content, at least for free on YouTube. So something you're interested in, yeah, come along for the journey, and good luck. I will talk to you soon.